Hello everybody, this is Dr. Fu. Today we're going to talk about Module 5A, the CNS control in cockroaches. This is going to be part 1, and the objectives. First one, we're going to understand and successfully perform a microsurgery. And then we're going to develop an experiment using the hook electrode to determine the directionality of the action potential generated at the cervical nerve. Alright, this is the cockroaches that we're gonna use. They are South American cockroach. They are huge, very big, but they are really harmless because they have wings, but they cannot fly, and they cannot climb walls either. So, if we happen to have some of them escaped, they are not gonna propagate fast, so they are not that harmful. Alright, so here is some anatomies of cockroaches. First of all, same as cricket, they have sulcus. On their sulcus, they have a lot of hairs, and at the bottom of each hair, they have mechanoreceptors. That's how they interact with the environment. If somebody poke their cerci or there's a wind blowing on them, they will be able to feel that. So they will decide which way they should escape. If you cut them open, we're going to see their ganglia and connectives. So the connectives are basically the nerve cord connecting the two ganglia. And the connective and the connectives are basically the central system for cockroaches. The cockroach, they have head, but they really don't have much function. They don't do math with their head. In their thoracic region, they have 3 ganglions. In their abdominal region, they have 5. For the thoracic region, it is more of an escape center because their legs and wings are connected there. For the abdominal region, it's more of a signal transit and dissective center. So this is a picture of the cockroach's ganglion connectives. You can see there is a ganglion here, the yellowish structure. There's another one here, and there's another one here. The connectives connect between the two ganglions are the nerve cord. So there's one connective, and there's another connective. If you do a cross section of a nerve cord, you can see some bubble look-like structure here. They are the giant interneurons. Signals transfer very fast on these giant interneurons because they have bigger diameters, although they don't have myelination. Okay, so let's talk about the hypothesis we're going to have today. So we are going to test the hypothesis that signal generated at the cervical nerve will travel exclusively through the CNS to reach the thoracic ganglion. So two-part test. First one, the signal will travel ascendingly. Second, through the CNS is the only way to reach there. Okay, so how do we test it? This is the experiment design. So first one, we are going to hook our electrode here. This is going to be our recording site. Later on, we're going to generate some lesion here. So what is the experiment result is going to look like? Okay, so here is the expected result. First one, if we record here, we poke a cerci. If this part is intact, we're supposed to see some signal here because if the signal travel ascendingly. However, if we generate some lesion here, we cut here. If this is the only way for the signal to reach the thoracic region, we should not see any signal here. In this situation, we'll accept the hypothesis. And in the other situation, which means if we poke the cerci, we receive signal here. If we cut it, we generate lesion here. We still see some signals in here, which means the signal will have some alternative route. This way is not the only way. So signal may travel through the peripheral nerve system, reach either the ganglion here or ganglion here or ganglion here, will travel downward to the recording site. So in this situation, we'll reject the hypothesis that signal travel generated at the cervical nerve will travel exclusively through the CNS to reach the thoracic ganglion. All right, so here's the this is the experiment that we're going to do, and next we're going to watch a video to see how the experiment is being done.